MSU.
It's going?
So
It worked. It worked, guys. We've gotten started. Trenton's favorite.
You also get smaller class sizes for general classes.
No.
Well, for the presidential scholarship, yeah, I had one.
We're going to start on number 27 today. We're going to talk about some collisions. Bonky bonkies. Right, Trenton? Come on, you Trenton.
Let's go, it's snowing.
That's what I was actually when I was doing Coleman's assignment. He kept posting in class. It is due by 8:50.
It shows how robust our school is. That we don't have a snow day ever. And like FedEx wasn't even delivering yesterday. Maybe I'm wrong. What's up?
It was applying to your conversation, how we don't have snow days up here, like, whereas back in California, we got maybe a couple inches, and they shut down the entire North State.
Yeah.
For school, everything, plus power outs.
Yep.
Like, it's totally.
When I was in college one time, it wasn't even that much snow, but it was like let's say 12 inches in town, like a good foot of snow in town. It's in Maryland here, DC. And they would have a complete shutdown. And this is a road that our road in the summer, which is a constant stream of traffic. That's how this road was all the time. A big arterial road. Anyway, this was weird. You just walk out on the road, just kind of so. But guess what? There are only 2 entities that stayed open during this time. Guess what they were? McDonald's. Close. It was Domino's and 7-Eleven. Their managers were like, I don't care if all public transit is shut down, if literally everything is shut down, you're coming to work, bro. People need their Slurpees.
Slurpee goes in the Slurpee cup.
Slurpees. Okay, anyway. It was just weird that they were the only places. So yeah, had to go to Domino's for your food source. Okay, so anyway. Snow. Okay.
Cooper, do you think we'll play for that?
Where you guys going?
Well, we're here, but
No,
it's Steve. So it's not. Dude, they're over. They're over.
They're about to be 1-12 there. We don't change the way we're playing.
You're not wrong. Guys, start off the season.
Okay. This is before. So if you read the question, the way it's described is 2 things are going to collide. Okay? These blocks are before the collision. Block A is traveling to the right at 4 meters per second, and block B is traveling to the left at 8 meters per second. And block A is quite a bit heavier than block B. It's 3 times as heavy, but block B is going twice as fast. So if you had to guess right now, after the collision, when they collide, what do you think is going to happen? So something to think about. So maybe make a prediction. A clack sound. By the way, that's a good point. There will be a clickety-clack sound, which is a form of energy. So when 2 things collide, there tends to be, right? If you calculate how much kinetic energy does this system have, right? You might then go, well, if there's a loud sound or some heat is generated during that collision, then that heat is lost to the environment, and the blocks will no longer have that kinetic energy. Does that make sense?
Yes.
Yes. Okay. So anyway, you have before. Now it will depend on what materials they are. If these are if these blocks are made out of some rubbery kind of bouncy material, they might tend to retain their energy better than if they're made of something else. So here's before, and then here's the after. It tells us that after the collision, block B, good morning, Mr. Thompson.
Is Weasel here?
Yes, he is.
Who invited this kid?
Okay. Can we start just going when someone gets summoned? Just go, ooh, busted. That would actually be pretty funny. Until Mr. Thompson one day is just like, what is going on? Why do you guys keep doing that every time? Okay, so. All right. Now I guess it's not entirely clear where this block will go. The block could be going left, and the block could be going right. So take a guess. How do you think we're going to determine, once we do this calculation, how will we determine we're going to end up with some number, like we always do in this class, right? We calculate some calculation. Oh, V is some number. How would you know if how do you know if block A is going to the right versus the left? What?
Positive or negative?
Yeah, positive or negative, right? So if we end up with a positive V value, that would tell us that it's going to the right. If we end up with a negative V value, that would tell us it's going to the left. So for now, just like I kind of have a feeling that this guy is going to like overpower the lighter block. So I think he's going to end up going to the right, but I could be wrong. Okay. By the way, keep in mind there's the possibility in one of these. I think I've hammered out any mistakes, but it's possible when you write a question like this that you could have a mistake. What if you get a V of like 3? What would be the problem with V being 3? If somehow the calculation
Game speed?
well, it still would have lost some speed, 4 to 3.
Well, if you got V was 3.
If V was 3, so
Oh, yeah, so.
but if he was going 3, how would he be going faster than him? Right? That doesn't make any sense. Block A is to the left of block B, so maybe they're going the same speed. Like if they kind of stuck together in a sense, they could have the same speed. Just something to keep an eye out for. Does my answer make sense? So let's do it. There's a phrase that we're going to use a lot called conservation of momentum. All right, I'll even write it down because I'm such an overachiever. Conservation
Right there.
of. So we spent a long time talking about conservation of energy, right? Energy is conserved. Well, momentum is another quantity which is conserved in a lot of cases. Okay. Okay, so let's do it. So take the total. So what's going to happen is the total momentum of the system before the collision must be equal to the total momentum of the system after the collision. So let's calculate the total momentum of the system. It's going to be mass times velocity, 15 times 4. That's momentum 1. And you have to add momentum 2. And then what kind of number is that? Negative. So the difference between momentum and energy, one of the big differences is that momentum is a vector. So you have to take into account the direction it's going. Right? Whereas energy is not a vector. It's a scalar. So you can just treat it like a number. Okay? So does that make sense? This is the total, the initial total momentum. Okay. Now that what it means to conserve something is that it stays the same. So if this is conserved, then over here I'd have 15 times V plus 5 times 2. Go ahead and calculate that. Well, I do my attendance, which I forgot to do. I think everyone's here except for Julia. She's skiing? That's a good place to be. I'm surprised more of you aren't out there.
Well, I have this great thing called basketball.
No, they didn't get that much snow. It says they got 3 inches.
Yeah, same, already.
There's probably better days to miss school. Okay, so that's the initial total momentum. This quantity represented the final total momentum. So when you solve that, Because by the way, what do we got here? We have 60 plus negative 40. So there was 20 units of momentum before. Subtract the 10, divide by 15, and you get 2/3?
Yep.
Okay. Is it negative or positive?
Positive.
So, okay, so be very careful with, is this number positive or negative? That's gonna be really important. Okay? Because we want to know, yeah, is he going, because he could possibly have bounced backward. He could have bounced off and be traveling to the left. But it turns out he's going 2/3 of a meter per second after this collision. Okay, so does everyone feel okay about that?
Yep.
Make sense? All right. Part B says, is the collision elastic or inelastic? I'll give you a really simple definition of those words. Elastic means the total energy is conserved, and inelastic means it's not. That's it. Okay? Now, of course, there's degrees of elasticity. We're kind of doing theoretical stuff here. Because, for example, let's say a collision happens and 99.9% of the energy is conserved. So there was 100 joules before the collision, and after there's 99.9 joules. You would say, in real life, you'd say that's a highly, highly elastic collision. Almost all the energy was conserved. But we'll just, for theoretical purposes, we'll say if 100% of the energy is conserved, then it's elastic, and then if some is lost, it's inelastic. And then again, just sorry to, I guess, repeat myself, but what are some ways that you can lose energy? Or the system can lose energy? Sound,
Friction, heat.
yeah, maybe heat,
Resistance.
some heat. I guess, yeah, you're right that, yeah, if you throw an air resistance, you're never going to have the energy conserved. So in these questions, we're always going to have frictionless, airless systems. So what we're focusing on really is when they collide, they can impart some of their energy to like the air molecules around them. That's called sound. That's what sound is vibrations in the air. And also when they collide, their molecules will go jiggly jiggly. They might actually heat up a little bit. Isn't there some meme about cooking a chicken by just like hitting it with a stick over and over again?
Yeah.
There's like real physics there, yeah. When you hit something, you impart it with some internal molecular movement. That's exactly what heat
Does
is.
it actually work?
Has anyone ever actually done it?
I saw some guy on YouTube try it. He just mushed the chicken.
I think there was a guy who did a pretty good job. I looked it up.
There was a dude on TikTok that was just smacking the hell out of a chicken.
With a machine, he made a robot.
Okay.
That he could adjust the speed at which he snapped it. And the temperature was rising.
That's how you do it, yeah. If you calculate it, you'd have to have some sort of like a paint shaker or something. Like,
Who is this?
anyway, all I'm saying is when two things hit each other, there is a small amount of heat. That is some of that kinetic energy is imparted to internal kinetic energy, i.e. heat.
Activates the heat particles.
No, it activates the chemtrails. Now that's what happens. Okay, so where were we? So if we look at let's calculate the energy. So this is a really simple calculation. So we're just going to go, we look at before. So before the collision, let's see how much energy there was. There was a 15 kilogram block going 4 meters per second. And there was a 5 kilogram block going 8 meters per second. Now, do we need to care about direction for an energy calculation? Colin, let's put that away.
I was researching the
I
chicken.
know. Okay, so do we need to care about the direction? No, not for energy. So you'd go 1/2 mv squared plus 1/2 m, that's kilograms, v squared. What does that come out to be? So this is the initial energy of the system. Someone help me out here. What is this going to be? It's got to be like 300-ish. 2 something. 280. All right, do we feel okay about that?
So I just have to do the half.
Yeah, so that's how many joules are now think of you're like an accountant now. That's how much money's in the budget. And we're gonna see how much money was left at a later time. And if anything's missing, then you can say, well, some of that money or energy was stolen through sound and heat. So after the collision, we had final energy, because we had a 15 kilogram block traveling, how fast is he going? 2/3 meter per second. And then a 5 kilogram block was going 2 meters per second. And so my final energy would be 1/2 mass velocity squared plus 1/2 mass velocity squared.
Does not seem like, is it a pretty small number?
It could be, yeah. I mean, that number went way down, so, and
It's
this,
like 13.4.
so what you got? That makes sense, right? Think of these numbers. This guy got cut by a factor of 4. What does that do to your energy if your velocity decreases by a factor of 4? Divides it by what? 16. mv squared, right? So if that v, the thing that's being squared in the formula, if that gets divided by 4, the overall energy gets divided by 16. He's getting divided by even more than 4. So they're both getting decreased by by a factor of 16 at least, right? So the overall number is decreased by at least a factor of 16. Does that make sense? So in this collision, yes, like almost all of the energy was lost. It retained very little of the energy. So this would have been probably it's a highly inelastic. So energy was lost. So this is inelastic, highly inelastic. Inelastic collision. Okay. For part C, what's the center of mass velocity of the system before and after the collision? We'll answer that. So let's go before.
Sorry.
God, is that your ringtone?
No, it's this. I pressed the wrong button. My watch buzzes, and I was trying to turn it off, and then it has a 5
It's a very
ding.
jarring sound. It's better than that original iPhone text tone that was like the ultra high pitch. It would be like,
I still
they're just
have
like,
that.
oh, Aaron, no, don't. That is the worst. Whatever engineer invented that sound is the worst. What?
No.
Horrible, horrible. Okay.
I hate it when your phone's ringtone is your alarm clock.
How do you find this? How do you find the velocity of the center of mass of a system? What's the formula you can use to make it really easy on yourself? Remember, momentum is mass times velocity, right? Yes? So for the whole system, you can just write the total momentum is equal to the total mass. You can't really say total velocity, but you can say center of mass velocity. Does that ring a bell? Hopefully it does. If not, I don't know, something's going on. So do that calculation for the before. What was the total momentum of the system before the collision? 20, right? Does everyone understand that? So what was the total mass before the collision? Also 20. So the center of mass velocity was
1 meter per
1 meter per second. All right. Makes sense, right? They're moving apart, right? Or sorry, they're coming together. And it just so happens that if you track the center of mass, because he's 3 times heavier, even though he's going twice as fast, he's 3 times heavier. So, Colin, put it away. My goodness. This guy kind of dominates that interaction. And so the center of mass, that's why the center of mass is moving in the same direction as him. Does that make sense? Because he has more momentum. Anyway, how about after the collision? Let's tally up the total momentum.
22.
Right. I mean, momentum's conserved. It ought to be 20. So 15 times 2/3 is 10. 5 times 2 is 10. So the same calculation for the after is 20. How about the total mass? Still 20. Okay, so let's try to find the moral of the story, you know? So look at this formula we derived, right? In a collision, I guess as long as you believe that momentum is conserved, which we should, I mean, it's pretty fundamental. Now, that actually does raise interesting questions. Why is momentum conserved? You will not. That's some high level stuff right there. That's really getting into the nuts and bolts of everything. But anyway, will the total momentum of the system change if momentum is conserved? No, that's the idea, right? Momentum being conserved means this number is not going to change. Will this number typically change? No, not unless there's some weird magic wizard stuff going on that's making blocks disappear or whatever. So if this stays the same, this stays the same, then that should stay the same. Cool beans? Or Kate. You're gonna make it Kate. All right, guys, try 28. What's up, Winslow? Question?
Say like in a real life like application, this like if mass would be losing, like say 2 vehicles collided and like a part of the vehicle like got dislodged off, like would that count as like changing your mass then?
Yep. Or a good application is like a rocket. So the way a rocket works in outer space, in Earth, it's a little interesting because a rocket shoots. So a rocket, say trying to leave the atmosphere, right?
Yeah.
It shoots these particles, right? The fuel is through a chemical reaction ripped apart into like particles and ejected this way. The pressure ejects it out. And so in the atmosphere, there's an effect going on of, well, you're actually, there's billions of air molecules in the atmosphere, right? So you're kind of pushing off those particles, right?
Yes.
But there's also like a conservation momentum thing. You shoot a gas particle this way, and conservation momentum means the rocket's going to have some momentum imparted this way. What's interesting is once you get into say you're out in outer space, so say you got a spaceship, so this is on Earth, but now you're way out in outer space, and you're like, well, how does a rocket push itself forward? How would it slow down or speed up? Well, what's going to happen is it would effectively what is happening with the rocket is it would eject many particles, but just consider one particle. So say before the particle is ejected, this thing's 1,000 kilograms. And then it ejects a particle, right? Say it ejects 1 kilogram worth of fuel, shoots it out through combustion. Well, now the ship is only 999 kilograms. So I hope that answers your question. You could then calculate, well, let's say you shoot that 1 kilogram of mass out at 1,000 meters per second.
Yeah.
That's quite a bit of momentum. You may have just imparted roughly a meter per second of speed to the ship because that conservation of momentum has to be conserved. So there should be, hold on, unless I am stupid, there should be a problem in here where we're actually going to do a precise, so 35, we're going to actually do a more precise calculation of exactly that. See how that works. All right. Keep going on 28. It's already halfway through the quarter. We're getting there.
Spring break is slowly coming.
So we're a quarter of the way there.
I'm going to Salt Lake.
Summer. Right, Trenton?
Right.
Trenton knows.
So,
Trenton knows.
Mr. Hall.
Sup, bro?
Which do you prefer, summer or winter?
Well, I don't work in the summer, so
I've never flown.
for that reason alone. But if I was living my true bootstrap existence, then I'd probably prefer winter. I don't know, summer's pretty good though. They're both really good. It's hard to choose. Let me just go winter. I'll go winter. I have no allergies in the winter, which is nice.
Like late summer, early fall.
Yeah, it's hard to beat like late July. I mean, how do you top that?
well, you can press a button that gets rid of all the tourists. That would be a nice start.
You don't just leave early.
We see what time Winslow gets here every morning. This man is not a leave early guy.
I'm saying, man, if you live here and you're not experiencing the park, in my humble opinion, try going to bed early, wake up early, beat all the tourists there. You'll be out. Pick a trail don't go in the Highline Trail. Like pick a trail that's kind of off the beaten path, and then you won't see a tourist for 10 hours if you don't want. And of course when you come back, you're gonna have to get through them, but that to me is a small price to pay.
I know this summer when I got home from hiking, we left at like 4 a.m. in the morning, and it was just a solid line of cars all the way up to the going sun.
Leaving at 4? No way.
Well, granted, my friend stroked past me and I had to do it quickly.
That's purple. Press a purple button. Press the man wearing the hat button. The meme. What are you talking about? Doubt. Press doubt. Press F to doubt.
Mr. Hall, we were
There's no way you left at 4 and we're in a huge traffic
We
jam.
were up at Logan Pass at like 6:30.
Oh, okay. That was-
Well, yeah, to the left here. It would take about an hour.
I don't know. Well, okay. Just drive harder. Winslow, okay, maybe that's true. I'm just saying, 99% of the time for me, if I leave my house at 5, it's just smooth sailing.
Granted, it was a Saturday too, so.
It's like even running on Noah time, we can get it before the crowd. Noah is horribly inconsistent. Actually, he's consistently late.
Okay, so there's other good places, Jewel Basin, but I think Jewel Basin overall, crowd density wise, is probably the same as Glacier.
Yeah, Jewel Basin.
But same thing.
They have a good handful of, like, we saw a lot of people on the way out.
Unless you go
Yeah,
towards
it's-
like Wildcat.
Yeah, Camp Misery will be packed full of cars, but again, like if you leave your house at 5 or 6, you'll beat them, and then you're on the trail, and you might run into a couple people, but you're not going to be like.
Usually like Wildcat Lake and stuff is a little bit less crowded than like Birch and Mountaineers and stuff.
Not in the
Even Aeneas is one of my favorite, but I mean, yeah, you might see 20 people.
Yeah, it's not that bad.
It's not like being up at Logan Pass. Anyway,
So you gotta do Bishop's Path and just sit up there for like 2 hours.
that's a good one. That's one of my faves.
Bishop has some insane views.
Okay, who got this one? Who's confident in their answers? Aaron?
Just for the first one,
Sure. What'd you get for your answer?
2.4 meters per second.
Agreement?
Yeah.
Yeah, calculation should be pretty straightforward. You got the 30 kilogram is at rest, so 30 times 0. Block B is 20 kilograms and is traveling 6 meters per second to the right. Fair enough. Okay. By the way, let's put this on the back burner. What's the total momentum of the system?
120.
120. So this is before. Okay. And then after the collision, you've got they're traveling together. So the trick here is to say if they're traveling together, they have the same velocity, right? So I could say it's 30 times velocity plus 20 times velocity, or 30 plus 20 times velocity, right? So I get 120 equals 50V. How do we feel? So I agree with Aaron. It must be correct. Okay. Now, are we elastic or inelastic? Well, let's calculate the total energies. before the collision. Sorry, this was after. Who has a confident answer in the elasticity with the justification? Julia?
It's inelastic and it lost 216 joules of energy.
Okay. What did it start off with? It was
360.
okay, so lost like quite a bit, more than 50%. Is that
360.
so? Energy, you gotta go 1/2 mass velocity squared plus 1/2 mass. You said that was 360.
Mhm.
Okay. So this is our before energy. Okay. Make sure you show your calculations. So this is before. And then after, we had 1/2. I'm gonna just put the masses together. So 1/2 times 50 times. Does that make sense why I can do that? I can just lump the masses, kind of put a rubber band around them mathematically. And then what does this come out to be, Julia? What'd you get?
144.
Okay. So clearly we lost a good chunk of energy. Okay. And then center of mass. This one's yes, Aiden.
In the elasticity, so if we lose any, we're gonna call that, say we lose like 1 joule, we're gonna call that inelastic, correct?
Yeah, on a free response test, I might write something like technically inelastic, but that's pretty elastic though. Like, I don't know. That would make it pretty clear that you had the right idea. But so yeah, if you want to get technical, like every collision has some degree of inelasticity. There's always some sound or heat. But oh, okay, center of mass. How fast does the center of mass be going?
2.4.
2.4, right? You can calculate that, but then here's the thing. We already figured out that after the collision, they're traveling together. So where's the center of mass if two things are traveling together? Right? Like in the thing, right? So if two blocks are, yeah, so if two blocks are traveling together, the center of mass is like inside the blocks. So it must be traveling the same speed as the blocks. Anyway, so 2.4 should be your answer for C. All right. If trending gets any more energetic, we might completely lose control. So let's end a little early today.